So today we're going to be talking about trig functions with general angles, and this first section right here just kind of gives you an application sort of example for why what we're talking about today is necessary in certain situations. So I'll let you have some time to read that on your own later. But thinking back to what we have done so far with trig functions, everything that we have found for values have all been acute angles. So most of what we've done so far this year and also with geometry was with right triangles. And so everything was less than 90 degrees. Or in the case of radians, which we're kind of transitioning into, less than that value of pi over 2. So looking back at that previous equation, once you have a second to see that, you'll notice that you have to find the cosine of an angle that is greater than that 90 degrees or greater than pi over 2. So what we're going to be working with today is kind of extending that domain of trig functions to include angles of any measure and not just acute angles. So here is a chart that will be very helpful to you talking about trig functions that are in standard position. And essentially it is using the Pythagorean theorem to find the distance from the origin on a graph to whatever point P that you're looking for. And so as you can see, each of these labels over here for the ratio correspond to kind of those same things that we've talked about before. So if you're starting from the origin, you have the opposite over the hypotenuse for sine theta, adjacent over the hypotenuse for cosine theta, etc. And then these, again, are all of your reciprocal relationships. So you're just switching those or finding the inverse. So looking at this first example here, we want to find the exact values of those trig functions that we just looked at. So we have sine, cosine, tangent, cosecant, secant, and cotangent. And if we're looking at the values that are given to us here, we know that our x distance is equal to 5, and then y is equal to negative 12 to get us to this point. So we are going to use the Pythagorean theorem to find r. And so when you do that, you have the square root of 5 squared plus negative 12 squared, which is the square root of 169, which makes r equal to 13. So now that we have each of those values, we can find sine of theta that's supposed to be y over r, so it's negative 12 over 13. Cosine of theta is supposed to be x over r, so we're going to have 5 over 13. And tangent of theta, which is y over x, so negative 12 over 5. And then if we look at each of the inverse, we have cosecant of theta, where we're just going to flip this one over. So negative 13 over 12. And then we have secant of theta for this one. So 13 over 5. And cotangent of theta, or negative 5 over 12. Alright, one other set of angles that we're going to be talking about in particular today is what's called quadrantal angles. And these are the angles where their terminal side lies on an axis. So that occurs at 0 and also 360, which are the same spot, and then 90, 180, and 270. And so we know that if it's occurring on an axis, that one of my values, either x or y, is going to be 0. And since we can't divide by 0, since it's undefined, two of the trig values are going to be undefined at each angle. So in this second example here, we're going to be finding the values of those 6 trig functions that we just looked at, but for an angle that measures 270 degrees. So we know down here at 270 that x is what's equal to 0, and then y is equal to negative r. Okay, so if we have the sine of theta which is equal to y over r. Then we have negative r over r, which reduces to negative 1. If we have the cosine of theta, which is x over r, so this is 0 over r, that just becomes 0. And then when we have the tangent of theta, we have y over x. So this is negative r over 0, which is one of those undefined functions here. For the cosecant of theta, when we find the inverse, we're going to have r over y, which is still r over negative r, or negative 1. For secant theta, we have r over x, which is r over 0, so there is your other undefined function. And then lastly, we have the cotangent of theta, so we're going to flip this over, which becomes 0 over negative r, and so that one is just 0. Okay, so talking about reference angles, we have what's a non-quadrantal angle. So any of those that fall that are not 0, 90, 180, 270, or 360 will have a reference angle that is an acute angle formed by the terminal side of theta, or the angle that you're looking at, and the x-axis. So for instance, if I have 120 degrees as an angle, that's not an acute angle. So it would fall here in quadrant 2, where I could then find a reference angle that is acute that matches with that. So anytime that you are in quadrant 1, then your reference is the same as the angle measure, because anything in quadrant 1 is an acute angle already. If you're in quadrant 2, you're taking either 180 minus theta or pi minus theta, depending on if it's in degrees or radians. And then also in quadrant 3, you use 180 as that reference, but it's going to be the angle minus 180, so just flipped from what we talked about in quadrant 2. And then for quadrant 4, we're using the x-axis again, so either 360 or 2 pi as we make our way back to 0. So here's a couple of examples for us. The first one is a 300 degree angle. So it's actually already sketched for you, and anytime that you see this arrow, it shows you which direction it's supposed to go. So that shows you that it's actually an obtuse angle, and then this is your reference angle here. So since it lies in quadrant 4, I'm going to take 360 minus 300, and that reference angle is 60 degrees. Okay, so that is theta prime, or the reference angle. Then we have negative 2 pi over 3, which again is already drawn for us over here. And it lies in quadrant 3. So we can either use 2 pi and subtract our angle from here, or we can use the positive version of that angle. So since this went counterclockwise, since this went clockwise, we can go counterclockwise to get the positive version of that. So I'm going to show you both things. So we have 2 pi minus 2 pi over 3 to get you 4 pi over 3, which is the positive version. But again, that one is still not an acute angle, so it cannot be our reference angle. But if you look at the picture over here, 4 pi over 3 lies in quadrant 3. So we are going to take the larger 4 pi over 3 minus pi, which gives us a reference angle of pi over 3, because you can just make this 3 pi over 3, so 4 minus 3 is 1. The following table tells us what the sign of the function is in what quadrant. So 1, 2, 3, or 4, is it positive or negative? And that helps us to determine the trig value using those reference angles that we just found. Okay, so you have sine and cosecant that are positive in quadrant 1 and quadrant 2, but negative in 3 and 4. You have cosine and secant that are positive in 1 and 4, because that has to do with your x values, and then negative in 2 and 3, and then tangent and cotangent, positive in 1 and 3, and negative in 2 and 4. Okay, so always determined by x and y because r is always positive, since r is the distance from the origin. So to find the value of any trig function with any angle, you first want to know the reference angle. Then you're going to find the value of the trig function for the reference angle and use that angle to determine if it's positive or negative. So, in this first example, we have the sine of 120. And so the terminal side of that angle is in quadrant 2, as we can see by this picture over here. So to find that reference angle, it's actually already written in the picture as well, but if it weren't, we would take 180 minus 120, which gave us 60. So then I am going to find the sine of 60 degrees. Which, if you refer back to your table of trig values from 13.1, or just your knowledge of special right triangles from geometry, you can get any of the measurements that we needed for 30, 45, or 60 if you don't remember those. So the sine of 60 in that table, it will tell you, is the square root of 3 over 2. And since that lies in quadrant 2, using the table that we just looked at, our sine is supposed to be positive in quadrant 2, so we leave it as the square root of 3 over 2. Now, for the cotangent of 7 pi over 4, we see that that terminal side is in quadrant 4. Okay? So, once again, I am going to take 2 pi, since it's either 2 pi or 360, and I'm going to subtract 7 pi over 4. So this would be 8 pi over 4 minus 7 pi over 4, which leaves me with pi over 4. Okay, so I'm looking for, since it's negative in quadrant 4, by the signs that we just talked about, the negative cotangent of pi over 4, which is the same as 45 degrees. So if you need to go back and review that table, cotangent of 45 is 1, so then our final answer will be negative 1. So a lot of these, until you get to memorizing or kind of knowing where each is located, is going to depend on you referring back to the table from over here that we just talked about with the positives and negatives, and also that table from your right triangle trig notes from earlier this week. Alright, so wrapping up our last couple of examples here, looking at if we are only given one of the trig functions and asked to find the other 5 trig functions, how we would go about finding that information. So in this example, we have the secant of theta, and secant we know is r over x. So that means that negative 4 over 3 is equal to r over x. Well, we know that r always measures the distance from the origin to whatever point that we're looking at on the angle. So r cannot be negative, which means r is 4, and x has to be equal to -3, making sense with this diagram over here because in this direction x is negative. So this -3 is based on location. Okay? So now we're going to use those two to find y. So Pythagorean theorem tells me -3 squared plus y squared should be equal to 4 squared. So then y squared is equal to 16 minus 9. So y is either plus or minus the square root of 7. Again, going back over here, we see that the y values are negative in quadrant 3. So then that means that y has to be equal to the negative square root of 7. So now we have the information that we need to find our other trig functions. So sine theta is going to be y over r, so negative square root of 7 over 4. Cosine theta, which is x over r, so it is -3 over 4. And tangent theta, which is y over x, so that is negative square root of 7 over -3 is what it should be, which is the square root of 7 over 3. And then we're going to find the inverses of each of those, where it gets a little bit trickier when we have that radical there. So for cosecant of theta, we have 4 over negative square root of 7. So I need to rationalize by multiplying by the square root of 7 on the top and the bottom. So that gives me -4 square root of 7 over 7. And then secant of theta is -4 over 3, and cotangent of theta is 3 over the square root of 7, which comes out to be 3 square root of 7 over 7. In this last example, we kind of take away that coordinate plane with the different quadrants, and we have to figure out, based on the information that's given to us, how to solve for the missing measurements. So it says, in a robotics competition, a robotic arm is 4 meters long, and it's supposed to pick up an object at point A, over here. Release it into a container at point B. And the arm has been programmed to rotate through an angle of precisely 135, so that's labeled there for you. We want to know what is the new position of the object relative to the pivot point. So think of this as an XY coordinate. And so we have 0, 0 here. The point for A, since it doesn't go up or down at all, is going to be 4 units to the right, so +4 and 0. We're trying to find a point for B. Okay. And going back to our reference angle discussion from earlier, we know that this would open and lie in quadrant 2, so my reference is going to be over here with 180 degrees. So I'm going to take that 180 and subtract 135, which gives me a 45-degree angle measure. Okay. Then we're looking at the location of B. So again, on a graph, it would be in quadrant 2. Thinking about those points, x and y, we know that cosine is negative in quadrant 2, and sine is positive. So in order to find the cosine of 135, we're looking at the negative cosine of this reference angle. So negative cosine of 45. If cosine is x over r, then the negative cosine of 45 is going to be x over 4, because that was the distance that it had moved from the origin. Okay. We also know that cosine of 45 is the square root of 2 over 2, referring back to our table from 13.1. So then, if it's negative cosine of 45, it's negative square root of 2 over 2. If that's equal to x over 4, times the square root of 2 is equal to x when I multiply that 4 over. So now, I'm going to go back up here. Sine of 135 is equal to y over r. We know that the sine of 45 from earlier is equal to y over 4. Sine of 45 is also square root of 2 over 2. So then that is going to be equal to y over 4. Multiplying by 4, I get 2 times the square root of 2 is equal to y. So the coordinate for b is negative 2 square root of 2 and 2 square root of 2. And 2 square root of 2 comes out to be, as a decimal, about 2.83. So if you're talking about the new position relative to the pivot point, then we have moved 2.83 meters to the left, so this way, and now we are in front of the pivot point since it moved up. So this is ultimately the answer that they were looking for.